Hello everyone and welcome to my channel. Imagine taking the engine, transmission, driveshaft and differential in your car and throwing them all out. What do you do with the space left behind? This brings us to today's protagonist, the in-wheel motor. Simply put, it's about stuffing the power source directly into the wheels. When many people talk about in-wheel motors, most think its advantages are getting rid of the engine and the transmission, increasing interior space, or improving transmission efficiency. But these are just the most superficial physical attributes. As a vehicle engineer, in my view, the true revolutionary significance of the in-wheel motor isn't about saving space. Instead, it is the ultimate solution for vehicle self-regulation in the area of autonomous driving. First, let's take a look at the structure of the in-wheel motor. The first part consists of the brake disc and the brake caliper. Although in-wheel motors can achieve regenerative braking electromagnetically, a traditional mechanical friction braking system remains essential to ensure absolute safety. They are cleverly and compactly designed on the innermost side of the motor. Right next to the braking system is the silver protective cover. Acting like a shield, it protects the fragile electronic components inside from dust, mud, and gravel. Inside the protective cover is the brain of the entire motor, the power electronics and the capacitor ring. They are responsible for receiving commands from the vehicle, controlling the conversion and output of electrical current, and precisely adjusting the motor's speed and torque. Integrating the controllers directly inside the motor significantly reduces the wiring space that would otherwise be required in the vehicle body. Next, we see the core components that actually generate the power. First is the stationary stator, which is wound with denser copper coils. When an electrical current passes through, the stator generates a power rotating magnetic field. The bearing in the center of the stator plays a crucial role in connection and support, ensuring that the external components can rotate smoothly around the stator with low friction. The blue component wrapping around the outside of the stator is rotor. This is a typical outer rotor design. The rotor is equipped with permanent magnets, and under the alternating action of the stator's magnetic field, it is pushed to rotate at high speeds. Finally, the rotor is directly connected to the standard wheel and tire. Without complex mechanical transmission components like traditional drive shafts and differentials, the power generated by the rotor achieves true zero-distance transmission. It directly drives the tires on the road, resulting in extremely high transmission efficiency. In summary, through this highly integrated, layered structure, the in-wheel motor perfectly packs complex mechanical and electrical systems into a standard wheel. I'd like to cite a paper by Kasuyama, an engineer at Toyota. In this paper, he provides a systematic explanation of how in-wheel motors can be used to achieve full body posture control. First, let's look at Figure 1a. This is the yaw control we are most familiar with. The principle is simple. Brake on the left side, drive on the right side. By utilizing the difference in the wheel forces between the two sides, we make the vehicle body rotate, just like a tank. This is the torque vectoring control that most current electric vehicles are doing. But this is just the tip of the iceberg regarding the potential of in-wheel motor. The real magic happens in Figure 1b. Please focus on this point, the suspension rotational center, and this crucial angle, theta. In traditional understanding, driving force is only used for acceleration. But in this diagram, you can see that because the suspension is not horizontal, but has a specific angle theta, when we apply driving or braking force, this horizontal force splits off a vertical component, Fz, along the suspension link. This means that the moment we step on the accelerator, we aren't just pushing the car forward. There is actually an invisible hand lifting or pressing down on the vehicle body through the suspension. Using this principle, we can control the vehicle's pitch and vertical height. Finally, let's look at Figure 1c. Once we master the method of generating vertical force, roll control becomes a matter of course. We can make the left motor generate a downward pulling force, while the right motor generates an upward pushing force. With this push and pull, the vehicle can actively resist body roll during cornering, or even actively lean inward. So, as long as we make good use of the suspension's geometric characteristics, the in-wheel motor is no longer just a power source. It transfers into an active suspension system, achieving full body posture control over yaw, pitch, and roll. Finally, let's discuss the challenges brought by in-wheel motors. The main issue is the increase in unsprung mass. Unsprung mass includes the suspension, wheel, tires, and the braking system. An increase in unsprung mass leads to a decrease in vehicle ride comfort. Here are two papers that focus on how to solve the problem of increased unsprung mass caused by in-wheel motors. I will explain the papers mentioned in this video in detail in future episodes. That's all for this episode. Thank you for watching and see you next time.